All right. So, hi everyone. My name is Peter. I'm a data engineer at Wise, and today Abdullah and I will share how we are in the process of transitioning our analytical workload to a modern open source data lake stack using Iceberg and Trino. So, before jumping into the details, I want to show some metrics that, Wise is a global financial service company specializing in money transfer, for someone who don't know. And to give some scale of the business, you can see some metrics about the company. So we have roughly 30 million of users. We moved across the globe $150 billion between our customers. And Wise as a business is a rapidly growing business. So we are expecting some growth in the future as well. From the data's perspective and how we work with data at Wise, I want to show some further metrics. So in general, at a company who's directly or indirectly connected to data, producing data, we can summarize them up to more than 100 engineers. It's including product engineers, analysts, data scientists. Everybody just contribute to our data volume. We have roughly 50 engineers who taking care about the platform itself, the data platform. So they keep building, maintaining, and running the underlying data infrastructure for our users. And in data lake specifically, we have roughly 10 engineers who contribute regularly into the data lake project that we are talking today. So regarding data volume, in scale of analytics, so for our analytical use cases, here are some metrics that our data volume in analytics is roughly 1.5 petabytes. We need to serve 800,000 analytical queries per day, and it's keep growing. Regarding how we are solving this requirements, we currently using a cloud data warehouse provider, but does job. But we always wanted to have something open source and that based on some open source technologies. But we had some problem with that for a long time, which is basically the table format. And traditional data formats for data lakes like Parquet files, Evro doesn't really work for us because one of the main criteria that we have is basically using ASCII transaction and specifically the upsert capabilities, which is the nature how we work. We can't really live without upserts. So we had to find a table format which fulfill all of these criteria. And also we wanted to have near real-time ingestion and query capabilities as well, which wasn't really possible with the traditional table formats. And we started testing the new table formats, including the Iceberg, Hoodie, Delta. And after all, we decided to go with Iceberg. We decided Iceberg because it checked all our or ticked all of our checkboxes, and we also find a nice open source community behind it, and we were happy to see that all of our vendors looking into Iceberg as a strategic project. So we really find Iceberg is a table format that we want to go with in our new data lake infrastructure or architecture. So this is how it all started. We selected Iceberg as the core component of the data lake. We backed it up. So Wise is running primarily on Amazon. So it was obvious choice to use S3 and Amazon Glue as storage and data catalog. So this was straight. And after that, we started further building blocks around it. And this is how it looked like at the end. Let me go through one by one. So from the ingestion part, our data sources, I would categorize into three buckets. So first, we have a lot of Kafka topics that we need to ingest into the data lake. We are talking roughly about, I don't know, more than 1,000 of topics. And we have MySQL and Postgres data sources, actually MariaDBs. We're talking about roughly 300 each. And to move the data in a streaming fashion from these sources to lake, we created an infrastructure or a framework on top of Link and Flink CDC. This is the core behind our streaming. This is the core engine behind our streaming pipelines. It does the job really, and we are just happy with Flink in general. And Iceberg optimization is an important bit here because, yeah, we know that once we have the Iceberg, that Iceberg tables needs to be kept maintained, optimized regularly. It's a big task, and we use Trino and Spark in parallel for that. We run several tests using the two. Sometimes we find Trino performs better, sometimes Spark, and both project keeps developing rapidly, so we are happy to see that. And what we did is we created a framework of top of two, and we can switch over which one performs better regarding specific optimization tasks. And in the future, let's say if Trino keeps adding more and more, or being developed more and more, we will be able to switch to go Trino only or Spark only, whatever. So this is from ingestion side. Consumption side, one of the big item is transformation. So our transformation in the lake is driven by dbt, Trino, and Airflow combo. I want to specifically highlight dbt here. So we're using dbt for some time, and it's really nice in dbt in general that we can change. So same dbt models works with minimal changes with different underlying data technologies. That's what we saw with this exercise as well. And it was really nice to see that the existing dbt models with small changes seems to be running with Trino as well. On the query engine side, yeah, Trino is obvious choice now, but we have Snowflake as well. Snowflake is our primary data warehouse provider. We need to use both, and luckily both having capability to read Iceberg tables, so we want to use both at the same time. Access control and data governance is an important bit. I don't want to go into the details here because it's primarily in-house built tools, but it's very, very important component for us. We are dealing with people's money. We are a regulated company. It must be there, and it's very important piece. So once we reached that point, we started putting into some data. So we started loading some data from Kafka into Iceberg and optimizing it and started querying it. And we started doing some performance tests, especially in the query engine side, just to know that which one performs better, which one more cost effective, how we can compare the similar query engines to get there. So in our performance test, there were three query engines, Trino, Athena, and Snowflake, not because these are the only choices. We selected these three because this was the most obvious choices for us. So Trino, which we are building infrastructure on right now. Athena, managed Trino from Amazon, and we are running everything on Amazon, mostly on single Amazon. And Snowflake, our existing data warehouse provider. But when we started measuring performance of each, it was not very straightforward because of the different, not very straightforward finding a good metric how to compare the performance of each, because they have different pricing model, different scalability methods, and we came up with a metric that we called cost normalized performance. That basically means that what a certain technology gives us if we give the same amount of money to each. And we run certain tests based on our using our own query pattern and trends. And this is what is, so I will show a few slides. So this one is comparing the single table operations, aggregation, filtering, and some bit more advanced window functions. So what this chart shows that, so the bold red line represents the same budget in each option, and the performance what that amount of money buys us. So in the case of Trino, that means that for single table aggregation, I'm talking billions of rows here, it buys, the target budget buys us a mid-size performance, but by adding more resources, we can scale up. And the arrow here always means the direction of the scalability if we put more, if we add more money into the technology. So Trino performs like if you add more resources, it scales out, scales up, and queries running faster. Nice, this is what we want to see. Athena has a different pricing model, and what we're seeing is not really the best choice for our query patterns and our use case. Because, yeah, you know, Athena is more or less always auto-scaling. It comes with a similar entry point, but based on our queries, so we need to serve nearly 1 million analytical queries per day. The more queries that we need to run, so Athena operates more like in a pay-as-you-go fashion, and the more queries drops this cost efficiency. Not really a performance. Performance may be more or less the same, but cost-wise, running that volume of queries for us, not the best option. Snowflake, Snowflake from scalability perspective, very similar to Trino. We like it. The thing is, if we add more resources or we buy more compute resources, compute capacity, then queries running faster and we can scale it very nicely. And this is what we always want to do, because some queries we are okay to wait more and pay less. Some other queries we are okay to pay more, but because we want those queries to finish faster. So we want to have this capability of playing around with cost and performance. The only difference is that the red line is a little bit lower here than Trino. That means the same budget buys a bit lower performance than Trino. So next steps was large table joins. It's pretty similar to the previous one. Trino and Snowflake gives the same scalability capabilities that we want to have. The entry point for Snowflake is a bit more expensive. JSON queries. JSON queries is the one that it shows out as complete opposite. Clear winner here is Snowflake. And why we need JSON queries, first of all? We work a lot with semi-structured and completely unstructured data. We just can't live without JSON queries. We have a lot of unstructured data. And Snowflake does a pretty good job with that. And doing the same thing with Trino, it's not as great. But to be fair, it's not really because of Trino, but the variant column type, which exists in Snowflake, but not really exists in Iceberg. And for someone who doesn't know what variant column is, a specific column type, that is designed for semi-structured data. And if you write a query so it's not like a simple keeping the data as a JSON string. So Trino, for example, if you run a JSON query, then it will scan all the JSONs one by one, not as fast. But on the good side, the new version, if I'm not mistaken, Iceberg version 3, variant will be supported very likely. So we're expecting some some good news here during the next week, and we hope that Trino will support variant in Iceberg too. And this chart will change a bit. Concurrency-wise, this was our last test, but very important again for us. Here is what we're seeing is similar to the first two charts. Trino, for us, without concurrency requirement, perform the best. It starts with quite high performance capabilities, and by adding more resources, it can deal with concurrency much better. Athena is having the same problem for us, at least. It always try to auto scale, but adding more queries makes less cost efficient for us. And Snowflake, again, it just comes with a lower entry point. So this is regarding performance and how we think about data lake at now and what we are into. And next, I want to ask Abdullah to talk more about technical details about our Trino implementation and how it fits into our data lake and how it's been set up.
Thank you, Peter. Hi, everyone. My name is Abdullah. I'm a member of the team at WISE working on the Data Lake initiative, focusing mainly on the Trino integration into our infrastructure. I'll start with a brief description of how we started the Trino adoption. Then we'll talk a bit of about how things look now, and then share some thoughts and ideas around things that should be considered when working with Trino and Iceberg. So to start, this was our early simple setup. Before this, we had like a classic warehouse setup where data is replicated from different sources into the warehouse. Two things here. So there was the cost part. We wanted to try to contain the cost of the warehouse service, and we wanted to provide more near real-time analytics capabilities to users. So we started experimenting with Trino as a distributed query engine. And the initial setup was simply to query data from our different Kafka clusters and to use the existing warehouse mainly for data enrichment. Now, the problem here was with the reliance on the compute resources of the Kafka clusters. So running heavy queries on the Trino side overloaded the compute resources on the Kafka clusters. We mitigated this by introducing quotas on the broker side, but this means that queries will be running slower on the Trino side. The other thing is it was hard to map a Kafka topic to a Trino table. So some more complex queries were actually impossible to run on Trino side. It caused different kinds of issues. One of them was, for example, the schema evolution just failed with self-join queries. There were many options to consider, but based on the things that Peter mentioned about why we selected Iceberg, we moved with Iceberg as a data source. And this is how things look like now with our Trino setup working with Iceberg. So in the middle, you can see that we have multiple Trino clusters running on K8s to handle different kind of workloads. All of these clusters run behind the Trino gateway, which has an amazing routing engine, which can route queries based on different things like data source, query type. So it's an amazing routing engine. On the left side, you can see that we connect to Trino using different clients. Maybe one thing to highlight is Superset, because this is what is currently used by our analytics team or by analysts in general. So we wanted to maintain the same experience. We also have services connecting to Trino to run some lookup queries. There's a small issue with this one, which is mainly managing the service account credentials. For now, it is all done manually, which can cause some issues and has some risks. So we're still trying to figure out a way to automate this flow, basically to create and maintain and share the service account credentials. On the right-hand side, we have the different data sources. We still have direct access from Trino to our Kafka clusters, but this is only for troubleshooting and debugging, mainly for engineers who want to debug issues with services in relation to Kafka messaging. We also have our current warehouse as a direct source for Trino, but this is not heavily used, and I will explain why in the next slides. We also use Trino clusters for running optimization tasks on top of the Iceberg tables. And as Peter mentioned, we have like two options. It's either Trino or the Spark on EMR. And I think based on some benchmarking, we noticed that the Trino performance is better for smaller data sets, mainly because of the startup time for the Spark step on EMR. Another thing that it's mostly like a custom plugin that we added to our Trino setup. And this was actually inspired by a talk from last Trino Fest. So this is useful in getting like runtime details about running queries on the different clusters. So we have a custom query history plugin that collects all these details and replicate them into an Iceberg table. And this Iceberg table is used on Superset to build different kinds of dashboards to keep track of the query performance and maybe to highlight some bad queries that can be enhanced. There's also the requirement to integrate all of this with our security and privacy infrastructure. So basically, we need to maintain or keep using the same services for access management. So we have a crawling service that periodically collects Iceberg table details from Glue and make them available as assets into our access management service. And we have another service that transforms these access management records into Trino access rules. We've also added a custom group provider plugin on the Trino side as well, so that we can move all the group access management to the access management service. We are still in the pilot phase. So at this phase, it's not like it's only like a small part of the workload switched to Trino. So we currently have 4 Trino clusters running over staging and production. Both clusters have a total of 54 workers now, but this thing changes up and down based on the usage on the cluster. These clusters run a total of 35,000 queries a day, scanning 4 billion rows. Again, this is just the pilot phase, and based on the numbers shared by Peter in the beginning, I think soon this will be much larger. A few things to consider. So I'd like to go over these points when adopting Trino and Iceberg in general. A few things about like managing the migration phase, some points about access management, and some points about auto-scaling. So for the migration phase, we had this plan initially to try to have like a gradual migration to Iceberg. Mainly because we have a huge set of data, and it cannot happen overnight. So we wanted to have like a gradual migration to adopt Iceberg along with our existing warehouse. So we wanted to try to see if we can actually do some cross joins between the different data sources. And this does not seem to scale well, mainly because of the fact that the Trino connector for our warehouse is a JDBC-based connector. And I think it's a known thing that for JDBC connectors, they mainly support a single split for obvious reasons. There's no like clear or a standard partitioning logic for these tables. So there was this scale limitation. We cannot run large queries on top of the existing warehouse. So we added like our customization, like we added an implementation on top of the connector to support virtual partitioning, to be able to create or to generate multiple splits. But this means that it will all be now dependent on the compute resources of the warehouse. which means that it can get even more expensive. The other option to try to do like a gradual migration is to use the existing warehouse's query engine to query both Iceberg and the native warehouse tables. But there's a problem here, which is about the incomplete implementation of the Iceberg specs. So the current warehouse has support for Iceberg tables as external tables, but not all Iceberg specs are supported. So the thing we're experimenting with now, which is like a short-term alternative or solution, is to use Trino to write Iceberg data. And this seems to be working based on the POCs we have done, mainly because Trino seems to write the Iceberg tables in a format that is actually recognizable and queryable by the warehouse query engine. So in order to make this scale, we will be using Flink to write or to replicate data from different sources into Parquet format. And then we will have Trino reading from the Parquet data and writing it into Iceberg. Here, the Parquet files are mainly just a cache. So this is only to try to keep the performance as good as we can. Again, this is just a short-term solution. The long-term solution will be to try to speed up the data replication into Iceberg by introducing by finalizing the CDC pipeline. Another thing is about access management. So, so far, we've been relying on Trino access rules to define the access management, to control the access management for the Iceberg tables. But the problem here is the separation between the rules and the Iceberg catalog. So basically, this means that we will have to do more work on Trino side just to keep the access rules up to date with any changes to the Iceberg schemas or tables. Having them tightly coupled with Trino means that we will need to do the same for any other query engine. So this is very much a query engine dependent task, which is a big overhead. Luckily, recently there was a change or a new feature introduced into the Iceberg specs. So basically, access rules will be embedded within the Iceberg catalog, which means that using a REST catalog, all the access rules should be part of the Iceberg catalog, so that now it's independent of the query engine and should be very close to the data source. Another thing to consider is with auto-scaling. So this is mainly to like utilize resources and to try to control costs a bit. This all depends on the workload. So so for some analytical workload, there's some clear seasonality. So we know that there is some high usage and some low usage. For example, this chart is from one of our existing warehouses where we can see there's like a pattern where over the weekends there's a much lower usage than the weekdays. So for these cases with like predictable workload or non-workload pattern, we can go with scheduled auto-scaling or Chrome-based auto-scaling. For less predictable workloads and queries that are more compute resource intensive, we can go with vertical pod auto-scaling. And for queries that are more like network intensive, we can go with horizontal pod auto-scaling. In all cases, we have Athena as a fallback, so that on the client side, there is this logic in case a query is not fulfilled within a specific timeout, the client automatically falls back to Athena. This is like, I think this is like a temporary measure for now until we have well-scaled Trino clusters. And it has been an exciting journey. I think it will be a rewarding one as well. Thanks to all the efforts from the communities of both Trino and Iceberg. Please, if you have any questions, share them in the chat. Thank you very much for your time and enjoy the rest of the day.